This talk is dedicated to flow management. And first of all, we must discuss the notion of flow. What is flow? Because actually flows are used in networks since very old times, and they are used in many cloud software. The flow itself appeared as a tool for network diagnostics more than 30 years ago. And only after that time, only after passing about 10 years, it was used for controlling routes information. And it's interesting that I don't know how the situation is in Thai language, but in Russian language, we have one word which corresponds to flow, to flux, to stream, and to current. But English language has separate words for each meaning, because flux is a quantity, a stream is something flow, and current is more like sequence of flowing in instances. Yes, but in some languages there is only one word which means everything, and this creates some inconveniences. The first time flow appeared as a part of NetFlow protocol, which was invented in Cisco in 1995. And they use it only for monitoring of network data. And it's interesting that they use the term traffic, which is actually somehow connected to road traffic, and you will see this connection later. They defined flow as packets having same 8 parameters, like source IP, destination IP, and 6 others. And this sequence of packets was named as a flow. And you can see overview of NetFlow capabilities if you follow this link. And as I told you, only 10 years later, these diagnostic tools has evolved into had evolved into a tool for routing and forwarding. And there is an interesting survey which was conducted in 2018. The author of the survey tries to understand what does it mean flow, and how this flow is connected to electrical circuits, how this flow is connected to our world. And I want to draw your attention to the figure above. You can see the road, and authors of this survey, they put this figure to demonstrate their article. And they authors made 6 attempts, after which they came to the definition of flow. So if you want to manage something, if you want to work with something, you have to name it and you have to define it. And there is a saying in England, name it to tame it. Yes, if you want to manage something, you have to name it. So we will try to define flow from 2 perspectives. First of all, we can study RFC. RFC is a request for comment. It's like a standard in network and IT world. But standards proposed by individuals, by companies, and so on. So it's not a very formal way. And we will try to define flow mathematically, because there is a rigorous mathematical definition for a flow. I found several RFC which give definition for flow. Several definitions were found from Wikipedia, and one definition was found occasionally. So you can see this 4 RFC, which contain definitions for flow in networks. The first RFC 2722 defines flow as a portion of traffic delimited by a start and stop time. So flow is a transient value, so it lives only for a period of time. And it belongs to one of the metered traffic groups. So we have to define traffic group somehow. And what is traffic group is not defined in 2722. So we have to define traffic group. And there is no rigorous, strict definition for traffic group. So while this definition is good, it lacks some important properties. There is a good definition in RFC 3697. A flow is a sequence of packets, or it's much closer, sent from a particular source to particular unicast destination, and which is labeled as a flow. So we see that it's actually a sequence of packets, and which is sent from source and destination. So if we want to define a flow, we need notions of source and destination. And then there is the RFC 3917. And here they define flow as a set of IP packets, which correlates with previous definition, passing an observation point. There is no observation point in previous definitions. In the network during a certain time interval. Okay, and this one correlates with the definition number one, when we say that flow, something that lives between start time and end time. So it's a transient entity. And finally, RFC 7011. Flow is defined as a set of packets of frames passing observation point. We've heard about this in the network. We've heard about this during a certain time interval. So this is also known to us. And all packets belonging to a particular floor have a set of common properties, which is very similar to what was set in the definition number one, and which is similar to the definition by Cisco NetFlow. Yes, they say that flow is a sequence of packets having common properties. And as they listed these common properties, source IP, destination IP, and so on and so on and so on. And we can unite different definitions to create some more rigorous and more clear definition of a flow. So it is a part of traffic or transmitted data with common traits, which are called source IP or traffic groups or something else, passing through an observation point. So there must be an observer. There must be someone who observes this traffic. For a finite period of time, we show transientness of a flow and between source and destination. This is a flow, a part of traffic with common traits, passing through observation point for a finite period of time and between source and destination. If there is no destination of source, it's not a flow. If it's not transient, it's not a flow. If there is no observation point, there is no observer, it is also not a flow. And it's always useful to use some analogies. And I try to understand how this title flow arouse, and why we use word traffic, which is usually used for road traffic, for vehicular traffic. And it looks like this term arose in 1950 during the establishment of the traffic theory, when several specialists from General Motors tried to simulate and understand how roads work in general, and how can we manage cars on roads. While this work started in 50s, in 1960s, this road traffic theory transformed into theory for um, flow networks. And that's how the term for flow arose. And you can see in brackets, you can see references. All references are at the end of my presentation, so you can follow this reference to read them. And there were two, actually, there were two ways to look at flows of cars on roads. One is microscopic, when each car is tracked, and one is macroscopic, when an ensembles of cars are tracked. And it's interesting that the second approach was developed by a great physician and mathematician, Mr. Lighthill, who is known for his works in computational aeroacoustics and computational fluid dynamics. But as far as I know, actually, neither first direction, neither second direction succeeded in prediction of cars motion, because both approaches has some flaws and some disadvantages. And therefore, while people try to apply these approaches, for example, for modeling of crowds, there is a special branch of traffic engineering dedicated to traffic of crowds, which is used for modeling of cities. But looks like the most important thing is that all this theoretical work gave birth to ideas of flow in electrical circuits in computer networks. And this theory of flow networks was applied to computer networks in 90s. The first work, I think, is in the middle of 1990s, so 1995. Maybe I'm wrong, because I don't remember the year precisely. But modern works are listed in references 2830, and the first work, I think, the first work appears in 1994 by Hungarian scientist Szabai, who showed actually similarity between motion of cars and motion of packets. And this is a very interesting result, because actually similar phenomena are governed by the same equations and by the same laws, actually. And I think that's how definitions from car traffic came into definitions of packets traffic. And then his ideas was summarized and developed by Indian scientist Chaudhuri, who wrote with his colleagues a long book called Statistical Physics of Vehicular Traffic and Some Related Systems. And he showed that a range of phenomena are covered by the same equations. So actually, packets flows in computer networks, car flows, financial flows, people flows, molecular flows, any kind of flows can be described by the same notions, by the same equations, and by the same methods. It's very interesting. And with Chaudhuri, we come to rigorous mathematical definition of a flow. And flow is defined actually as a value or current, a number of vehicles or packets. It doesn't matter. Now we see that they are similar, crossing a detector site per unit time. And here we see correspondence with definition from some RFCs. So it's a transient value crossing detector sites or observation point per unit time. And what is different in this mathematical and rigorous definition is introduction of the word number. So actually, flow is a number. And it is defined on the edge between a source and sink. So actually, it is defined on a graph. So each network can be represented as a graph. Each vertex can be regarded as a source or sink. And the value of flow is bounded by the throughput. This is a very important addition, because if you have a maximum throughput of some edge on your network graph, then flow cannot go from source to destination, because it will stuck. And the sum of incoming fluxes is equal to the sum of outgoing fluxes. If you remember basic physics and Kirchhoff's law or divergence theorem, you remember that there is a correspondence to them. Now I try to compare both points of views and create some single definition from standards and from theory of traffic. So flow as a packets count, and we will see this definition at the end of the lecture. I'm sorry, but I want to point out that there is a deep connection between this theory and statistical physics. So if someone has passion to strong theoretical background, you can refer to works number 9 and 29. And depending on the context and depending on 2 points of view, flow can be a packet count, so it's like a diagnostic tool. It can be a forwarding rule, it can be an edge on graph, or it can be a structure in database which is used to represent 3 previous items, 3 previous emanations of a flow. And recently, I've listened to one interesting lecture from a Russian network engineer. And when I listened to him, I realized that actually flows are, in some sense, it's not a rigorous analogy, it's not a straight analogy, but in some sense, flows can be thought as a MPLS, because in MPLS you take source IP, destination IP, you take UDP and something else, and you assign a number to all packets that has the same attributes, and all packets that have the same attributes, they follow the same route. And the same happens actually inside virtual routers or switchers. You take packets, you take their headers, and if there are headers that have, if there are headers that have the same attribute values, they follow the same route inside this router or inside this switcher. And in MPLS, this is like global flows, because this label conserves within the whole network. So there is some similarity between notion of flow and MPLS. In our SDN world, looks like flows appeared in a work conducted by authors of NOx, software-defined network controller. You can see this evolution of citations about their first work, and looks like this is the first paper, because they have 2,561 citations. So that's a lot. I can tell you that's a lot. And it's interesting that authors justify why they selected flow-based forwarding rule over packets-based or prefix-based. And they tell that if we define rules per packet, then if we have a granularity per packet, this would create too much CPU load. If we have forwarding rules per prefix, so if we define rules for forwarding using only source and destination IP, then this would be too coarse. We will not be able to manipulate our resources in networks accurately. And looks like the flows, the idea of flow is flexible enough at the one hand, and on the other hand, it doesn't consume too much CPU resources. So if you want to understand justification why flows were selected for SDN world, then you can refer to pioneering work like this one. And when flow started as when does flow begin as a forwarding tool? So allegedly that happens in 2003 when this gentleman proposed to use flows as a forwarding tool at the conference, the next generation of IP flow routing. And in 2009, he wrote a paper, A Radical New Router, which was published in IEEE Spectrum. And after that, flow came into network world as a forwarding tool. And in our vRouter forwarder, flows are used, I would say, at the end of pipeline, at the both ends of pipeline. When a packet, if you remember previous small talk, when packet arrives at the ingress interface, we take its header and we use it to decide what to do with the packet. And here flows are used to store this information. They store actually flows are used primarily to store what to do with packet, to store information about decision. But also flow tables are used at the end when packet egresses. I told you yesterday that there are two main regimes in which vRouter forwarder works. And we studied a little packet regime, packet mode, and actually the standard mode is flow-based mode, during which we decide what to do with packets and how to apply different security group and access control list. Packet mode allows us only to forward packets, and flows are used for security group, access control list, for net, for service chaining, and for other network functions which are needed. Therefore, you see that application range for flows is much broader than for packets-based forwarding. This is a figure which demonstrates in general how flow-based forwarding is applied in vRouter forwarder. I took this figure from Tungsten Fabric documentation, so you can find it on the internet. And you see that when, first of all, there is a difference between two states. In one state, we have packets coming from one virtual machine to another virtual machine, and both virtual machines reside on the one hypervisor. And there is another state when when each virtual machine resides on its own hypervisor. This figure corresponds to the case number one. When a packet arrives to ingress port, router forwarder takes its header, and it uses, it's written here that the router forwarder uses 5-tuple hash. This is wrong. Actually, it uses 6-tuple hash, including source IP, destination IP, source port, destination port, protocol, and VRF. Because let's imagine that you don't have VRF number, and you have tenants who have intersecting IP addresses. And in this case, if you have tenants with intersecting IP addresses ranges, there might be a situation when a flow from one tenant is applied to packets from another tenant, and you don't want to do this. Yes, that's why actually VRF ID is added to this tuple. It is added actually implicitly, so we can think of VRF ID, but actually we take not a VRF ID, we take a ingressing interface ID, but each ingressing interface ID is linked to VRF ID. Therefore, we can think of the parameter number 6 as an ID of VRF table. Therefore, when we have this 6 parameters tuple, we are looking up for flow. If we find this flow, then we take the decision for this packet. If the decision to drop, we discard this flow and we increase counters and so on. If the decision to forward or translate this packet, then we send this packet for next routines for another processing functions. And in OpenSDN, flow can be represented as a matching rule or flow key. So it's a rule which allows us to select packets. Then it's an action which is associated with selected packets: drop, mirror, forward, and so on. And actually, it is also called a state. So if you find flow state or flow action, these terms are interchangeable. And also flows holds additional information about source and destination, like MAC addresses, security group, virtual network names, quality of service, and many other. The key of a flow, which allows us to select packets, contains 6 numbers: source destination, source port, destination port, protocol, source IP, and destination address. Yes, six parameters. Well, and actually it can be a bit mask. So you can specify, for example, source port, but also you can say star instead of source port, and then this flow can be applied to all source ports. Or you can say source IP address specifying all bits, or you can specify only subnetwork, yes, and then this flow can be applied to all packets originating from some subnetwork. So you can think of this as a bit mask. OpenSDN forward denotes key, flow key, source destination interface using K and H. So each time when you type flow -L, you will see source IP, destination IP, and you will see K and H. And K and H corresponds to source or destination interface, which are used to distinguish flows from different tenants. And depending on a protocol, MPLS or VXLAN, depending on whether flow goes from one hypervisor to another, or flows starts and ends in one hypervisor. This KNH can be the same for forward flow and backward flow. We will talk about these types of flow a bit later, or they can be different. Therefore, you can use these hints to understand what kind of flow you see. Here are main states or actions of flows. You're familiar with drop, you're familiar with forward, and I hope you're familiar with network address translation. And there are two additional states or actions. Action hold. It means that a packet is put into buffer and waits for some condition. We will talk about hold action later. And mirror means that we must copy this packet. For example, we want to inspect a packets using some IPS system, and we don't want to consume CPU resource. We don't want to slow down connection. Yes, in this case, we create a copy of packets, and then we can analyze them separately on separate virtual machine or on separate CPU, while the original packet is processed as usually. And here is the most interesting part, which is missing in their documentation. So I recovered it from source code, from pieces of notes from different developers. Actually, OpenSDN has its own classification of flows. There is an ordinary flow, which totally correspond to our definition, which we made according to standards. So is a transient entity from source to destination, observed by someone, and so on and so on. This is an ordinary flow. But there is also fat flow. A fat flow is a flow where any parameter in its key is substituted with star. For example, when we spoke about this here, I told you that, for example, we can apply for a range of IP addresses or for a range of IP ports on UDP ports and so on. Therefore, when a flow is applied for a range of key values, then it is called a fat flow. And there is also a short flow. If you remember, we have a definition of flow of a sequence of packets coming from source to destination. And if our router cannot find this route, cannot find this edge between source and destination, then this is called short flow. And there are two types of flow. Forward flow is a flow which goes from source to destination, and reverse flow is a flow that goes from destination to forward, from destination to source, I'm sorry. Therefore, usually for communication, you always need two flows. If you send a packet from client to server, and it's expected that client receives an answer from the server, then you need two flows. Yes, you need a forward flow to send an inquiry, and you need a reverse flow to receive an answer. And as I told you, it's better to have some analogies in head. So first of all, flows have obvious analogy with rivers, yes, because rivers flow. If you consider small rivers, small tributaries like Nan, Pasak, then they are ordinary flow. They move ships from source to destination, one by one. If you consider large rivers like Chao Phraya, they unite river flow from different tributaries, and that's why they are fat flow. And if you put a dam preventing flow of water, so that ships cannot go downstream, you create a dam, and this is a short flow. That's how you can regard flows in networks. In OpenSDN networks, I'm not sure whether the same terminology is used in other controllers. But if you think about the ordinary flow, the analogy with river is absolutely correct. We can also introduce a notion of L3 flow, which is flow where any interface has INET type. When a packet uses L3 labels, when a packet uses L2 labels, but destination MAC is associated with L2 next hop, and for example, flows which are used for network address translation. So all these cases are listed on the slide. Now, what information is needed to organize flow forwarding? Well, actually, we need routes table, which links IP prefixes with next hops. Then we need next hops tables, because if we have links between prefix and a link between a prefix and the next hop, then we have to define a next hop itself. Of course, we need a flow table, and we need interfaces table, because interfaces ID are used as one of value of flow key. And we need functions to look up in flows. This information propagates via OpenSDN program in the next sequence. First, an operator or an orchestrator creates configuration inside config module. Then this information propagates to controller. Controller processes this information, creates routing information, local routing information base, sends it to the router. And we have the router split into the router agent. The router agent creates forwarding information base from routing information base and sends this information to the router forwarder. And the router forwarder creates its own flow tables, which are used for packets forwarding. But if you look at this figure, you will see that actually we see config, controller, and the router, which are physically separated. And actually, you now know that the router agent and the router forwarder are also physically separated. Therefore, information about flows is also separated between different modules. And we have a main flow table, which is finally used for forwarding of packets inside the router forwarder. And it's a hash table. And we have also some auxiliary tables, which are used for managing flows in the router forwarder. There is a flow table inside agent. There is a flow aging table and other tables. This is very important because when you analyze what's happening inside your network, you can monitor different tables. And the most problems comes from discrepancies between tables. For example, flow table in agent has an updated state, while flow table in the router forwarder somehow freezes. And this might create problems. The flow table of the router forwarder is allocated only once when agent asks the router forwarder about this. And some of you encountered this problem yesterday I remember that two of you who were doing tutorial encountered with this problem. They received error message on the first request, and this request corresponded to a situation when the router forwarder was not able to allocate memory for flow table. Even if you do not use flow regime, the flow table must be allocated. Then insertion and deletion of elements into this table is done by requests. Requests are formulated using XML language, and the router agent is responsible for formulating these requests using its own flow table. But actually, the router agent has two ways to interact with the forwarding table, which resides inside the router forwarder. It can send insertion or deletion request directly, but it can read this table using shared memory. We talked about ways how the router forwarder talks with outer world, and I told you that it has some auxiliary interfaces which are used to send information to the outer world. There is a netlink channel which is used to send or receive send request or receive response, and there is a shared memory which is allocated using a map Linux kernel call. What can we do with flows? First of all, we can install flow, so we can create it. Then we can update flow. We can evict. Eviction means it means that we destroy flow only in one direction. So we can selectively destroy forward flow or reverse flow without affecting another direction. And we can delete flow. It means that we destroy flows in both directions. So if you delete forward flow, the reverse flow will be deleted simultaneously. If you delete reverse flow, the forward flow will be deleted simultaneously. And flows can be analyzed. We can gather statistics from these flows. Flows are manipulated by the router agent, or you can manipulate flows manually using VR CLI utility. And those of you who have completed previous tutorial or who don't want to finalize previous tutorial can play with VR CLI utility today in order to study how flows are created or manipulated in the router forwarder. Here you can see a little more detailed explanation how flows are updated. Actually, we have a config which talks via controller with the router agent, and the router agent actually has OPA DB tables. OPA means operative tables, which resides in random access memory instant tables. And information from these instant tables go into flow engine, and flow engine programs the router forwarder. The router forwarder uses netlink to send requests to the router forwarder, the router agent use netlink requests to send insertion or deletion requests. It takes responses from the router forwarder. It also uses shared memory, as I told you, to inspect table, just only for read access. And it also uses PKT0 interface to receive packets for analysis. And this is a basic scheme how it actually happens when we want to create a flow. So each time when a forwarder see unknown flow, so a packet arrives at forwarder, and forwarder takes this header and sees that there is no corresponding flow for this header. Then forwarder takes this packet and directs it to PKT0 interface. And agent listens to this PKT0 interface. When it receives this packet, it takes its header and looks up into its operative database. In its operative database, it searches for routes, for next hops, for interfaces, and if all information is gathered, it creates a flow. If there is no information, for example, there is no such route, then it creates a flow, for example, with action drop. And it says to forwarder that all these packets must be dropped. But we remember that flow actually is a transient entity, so it lives only for some period of time. This is an important part of the flow definition. And the idea of separation of vrouter into vrouter forwarder and vrouter agent roots from simple consideration that forwarding program must be as simple as possible to forward packets, to switch packets as fast as possible. And complicated logic must reside in less performant part. So vrouter agent is less performant part, and vrouter forwarder is more performant and is more loaded, more computationally loaded. Therefore, there is no flow aging mechanism inside vrouter forwarder. So vrouter forwarder don't know how to terminate flows in time. This decision is created in vrouter agent. It has a separate table which is called flow aging. The analogy with H is simple. So each flow has a burst time. We set H time, and when some flow reaches time which is below its maximum H, then vrouter agent sends request to vrouter forwarder to delete this flow. And here is an updated version of our diagram how both programs communicate with each other. So actually, forwarder sends unknown header to agent via PKT0. Agent, using its flow engine, talks to operative database, and when it creates a flow, it sends request back to forwarder to install this flow with drop or forward or any other action. And forwarder answers to agent with the ID of created flow, because both tables must be linked together, yes, and a link is established using index or position of a flow in hash table. And at the same time, agent periodically, regularly monitors the flow table in vrouter forwarder using shared memory and selects flows for deletion. Each time when a flow ages, so the age of a flow reaches predefined time, agent selectively sends a request to delete this flow from forwarder. But reality is even more complicated, because OpenSDN must simplify our life, and therefore SDN must monitor changes in the network. For example, we had a virtual machine which resided on one hypervisor, and then this virtual machine migrated to another hypervisor. Obviously, the information which is needed to create a flow, to create tunnel, changed. And therefore, we have to update this flow. For example, somebody updated access control list, or somebody updated bridge routes table, or anything else. All changes that came from config must have corresponding changes inside the router forwarder, and the router agent is responsible for updating this flow table in the router forwarder. So each time when there is a change in config, this change translates into agent. This change translates into change in operative database, and then this change go into flow engine, and via flow engine, this update goes inside the router forwarder. Well, unfortunately, the screen is not too large, but if we put all places, all components of the router forwarder and the router agent on a 2D region, we will see some kind of map, and we will see step number 0 when unknown packet arrives at the router forwarder. Then we have a arrow 1 when we send packet for analysis. Then we analyze this packet and we send a response with new flow parameters from agent to forwarder, and forwarder finalizes this interaction between two parts by sending address ID, or it's actually a pointer, a pointer to place in hash table where this flow is stored. And now both parts knows that flow is installed, and they know the addresses of this flow in hash table. And if you are familiar with the TCP protocol, if some of you, or if you study TCP protocol in the future, you will find that actually this procedure has analogy with TCP triple handshake. There is a SYN request from client to server when we do TCP triple handshake, and there is a flow request from forwarder to agent. And then server, TCP server sends SYN plus ECK to a client, and agent sends reverse and forward and reverse flow to a forwarder. This is like SYN plus ECK. And finally, client must say to server about established connection. This is needed to receive sequence number. And we, in our vRoute agent, we also need to understand where this flow is installed, where it was installed, and where it was installed. And forwarder sends ECK, and it sends actually a pointer to the flow in hash table. And this is like ECK with a sequence number. So these procedures are equal. And despite I told you that vRoute forwarder doesn't interrupt flows in its own, it looks like there is one case when vRoute forwarder does this, is when it receives a packet with a TCP RST flag. Looks like in this case, vRoute forwarder can do this automatically without talking to vRoute agent. But I have to check this maybe again, but according to the source code, looks like vRoute forwarder can do this. But this is the only case when vRoute forwarder can interrupt flow without consultation with agent. And finally, a few words about flow establishment call stack and agent. So agent receives a packet. It takes its header, and then it analyzes its header. It analyzes, first of all, it tries to find a proper route. If route is found, it tries to analyze whether interfaces from both parts of routes are accessible. Yes, if we cannot, if there is no destination interface, then this is a short flow. So agent creates flow, even with forward rule, but it says short flow. And such packet is not, and the packets that corresponds to such flow are not forwarded inside the router forwarder. This is like a DEM. Then agent looks up for reverse flow. So if we receive request to create a forward flow, then we will need a reverse flow. If reverse flow is not found, then agent says, okay, forward, but short flow. And when forwarder installs short flow, and packets in this direction will be also blocked. And there are many other situations when the route agent can block flow, or it can modify decisions or parameters of the flow. And the final step is encoding. We have a special mechanism which creates a request from the route agent tables in the format which is acceptable by the router forwarder. This step is called encoding. And then we send information using SUN-DASH requests. When you work with flows, you must understand that we have two separate parts, two separate programs. And in our case, one program resides in user space, and another program resides in kernel space. So they are managed differently. And actually, both programs are multi-threaded. The route agent is multi-threaded, and the router forwarder is also multi-threaded programs. If we speak about the router forwarder, an access to its elements or prevention of data race or other unwanted situation which happens during parallel execution, prevention is done by atomic flags. First of all, flow KLIN, and second, just flags. Okay, is an H entry flags. So anytime when a flow is updated in the router forwarder, it actually uses special atomic operation which tests and modify values simultaneously. You can look for the list of these operations or operators, for example, in GCC compiler manual. And the route agent is written in C++, and its prevention of data race or deadlocks is organized using well-known mutexes, semaphores, and other instruments, which are, of course, are very well known for every one of you. And we can analyze what's happening with flow management using two tables. We can analyze the router forwarder tables directly if we go inside OpenSDN tools container. Or we can analyze this table from the router agent by going into introspect API. And we must remember that the route agent actually provides proxy access to the router forwarder table, but it can also show us its flow table, flow agent flow table. Let's call it in this way. So flow table in vRouter forwarder is created from flow agent flow table. So vRouter agent provides us access to both of these tables. You can see examples of requests, how to see these tables. And you can enter these requests in your laboratory. Actually, there are other tools for monitoring flows, like tracing is a tool which is used to store debug messages in random access memory. We can use introspect. We discussed introspect previously. And and I think, and there is an interesting tool which is called flow filter request, but unfortunately there is no documentation for this tool, so somebody should study the code to understand how it works. But it's a very useful tool because it allows to filter flows according to some predefined criteria. Here are a list of comments which we use to which we use to read flows in OpenSDN tools container. Usually we use flow -l to show all flows, flow -get to show information about specific flow, and if you want to delete flow, if you want to evict flow, yes, you use command flow -i. And this is very interesting because if you evict flow from vRouter forwarder, this information will not be propagated to vRouter agent until vRouter agent deletes it using aging mechanism. So this tool flow doesn't affect vRouter agent tables. You must know about this. And a few words about hold, finally. If we look at this figure, for example, this figure, I told you that a packet arrives at interface PKT0. This is a known packet. But what should we do with the packet, with a known packet? There are several ways to process this packet. Of course, we can drop it, but what it means? It means that if someone connects to a virtual machine and first packet is dropped, then it means that connection will be somehow reset. And this is not acceptable. What developers of vRouter forwarder decided? They decided to create a small buffer associated with each flow. Each time when unknown flow arrives, they take a packet belonging to unknown flow and they put this packet in this buffer. And while vRouter, and then they send this packet, the header of this packet for analysis. While agent is analyzing this packet, its copy is stored inside buffer. However, this the size of this buffer is limited because if we make this buffer unlimited, then we can easily we can easily consume almost all memory. Yes, we can create a large bunch of flow of unknown packets, send it to forward, and this will consume all memory. Therefore, the size of this buffer is limited actually to 3 packets. So only 3 packets are stored. Therefore, if a client sends more than 3 packets, then fourth packet, fifth packet, and other are dropped if this packet are unknown. And you can control the length of this buffer using sysctl utility. The packet which await inside this buffer has a hold state. The flow has hold state, and the size of this buffer can be controlled using sysctl utility. Finally, what the final most, I think, important takeaway from this talk. Now we know that flow can be used as a diagnostic tool, and it was originally used as a diagnostic tool. It can be used as a forwarding tool, but it also can be used as a prediction, modeling, and research tool. And a flow in OpenSDN is a rule for forwarding and inspecting a part of traffic with some common traits, which pass through some given observation point during some time interval and between a source and a destination. Okay, and bibliography is attached to the presentation. I think you can download it. That's all. And we can go for lunch.
I didn't end up on your topic right โอเค เช้าน่าจะหมดแล้วฮะ อันนี้น่าจะ ไม่รู้ว่าพอจะเข้าใจกันหรือเปล่านะแต่ว่าพูดภาพรวมก็คือเรื่องของการ management flow ทั้งหมดเขาพยายามที่จะเล่าว่า flow มันเกิดขึ้นมาได้ยังไงเรื่องแรกหลักการของการทำ flow แล้วก็ชอบตัวอย่างนึงที่เขายกตัวอย่างเรื่องของ flow ที่เป็น flat flow กับ single flow นะที่เอาแม่น้ำหลายๆสายมารวมกันอันนั้นคือ flat flow แม่ไหลลงมาแม่น้ำปิงวังยมน่านไหลลงเจ้าพระยาคือ flat flow ไอ้ flow ที่มาเริ่มต้นจากสายเดียวคือ single flow คือ flow เดียวแต่ความหมายของเขาคือโฟที่เกิดขึ้นเนี่ยมีไปกับมีอินเกตโฟที่เกิดขึ้นถ้าเกิดมีแค่ข้างเดียวไม่ครบโฟแสดงว่าคอนเนคชันไม่ได้ต้องมีโฟขาไปและโฟขากลับโฟขาไปก็คือโฟที่ครีเอทขึ้นมาจากอินิเชียลจากไคลเอนต์ทูเซิร์ฟเวอร์ขากลับจากเซิร์ฟเวอร์กลับมามันก็คือรีเบิร์ตโฟนะฮะแล้วก็ส่วนข้างหลังที่เขาพูดมามันก็คือเรื่องของการดิฟลงไปในหลักการในการ develop ซึ่งมันก็เป็นเรื่องของโค้ดละไอ้ที่บอกว่าflow entry อันนั้นคือคลาสหนึ่งของโค้ดเบสที่เอาไว้เก็บแล้วก็โอเวอร์เลย์เรื่องของแต่ละคลาสอันนี้ก็จะเซสชันเช้าก็น่าจะประมาณนี้เดี๋ยวเรามาต่อกันเซสชันบ่ายอันนี้เซสชันบ่ายก็จะมีเลคเชอร์แล้วก็ทิวตอเรียลเป็นแลบโอเคครับจบสรุปย่อๆมานี้ครับ